So I saw this question and figured that I can explain it without involving exponents too much. There are three switches which can be either on or off, or if you prefer, open or closed. They connect various resistors to a power supply, and what they give you is 2 to the power of 3, which equals 8 options. And hopefully I won't need to mention exponents again. What we'd like to know is how much current is flowing through the circuit. I'm doing things a bit differently today and recording as I solve it, so I don't know the answer yet. Something you'll just need to take my word on is that the current flowing through is equal to the voltage divided by the amount of resistance you have, and the total resistance for two resistors connected in series is equal to the resistance of the first one plus the resistance of the second one. I think I can provide some good reasoning for the rest of it. I'm also trying a few other things different today. Well, in addition to recording as I go along and not knowing if there's something else down the line that I'm not going to explain, I also put some art up and switched from the green virtual blackboard to black. I just feel that it gives me more color options, and I like being able to use green more freely. Okay, because I didn't plan everything through in advance, I've got to go back and add a few notes here. V for voltage and R for resistance is pretty straightforward. And I for current is a convention that's commonly used. Voltage is measured in volts, and resistance is measured in a unit called ohms, and current is measured in amps. And I am going to have a horrible time with audio editing and having so many starts and stops with different audio levels all over the place. So let's just define a few things here. We've got our power supply, which is the two lines there, and it makes the electricity go. The circle with the A in it is a current meter. It measures how much electricity is flowing. And the little zigzag sections are resistors, which reduce the amount of electricity flow. We also have open switches where electricity cannot pass through, and closed switches where electricity flows through freely. So the current that you have remains the same unless it's flowing through different paths, in which case the sum of the current going through the different paths has to add up to the amount of current that's flowing from the source. If we measure the voltage around our circuit at various points, the voltage will go up as we pass through the power supply, and then as the electricity flows through each resistor, the voltage will go down. And by the time we get back to where we started, the voltage has to be the same as when we were there the first time, and we can figure out how much the voltage drops across each resistor. When I said that current equals the voltage divided by resistance earlier, we can multiply both sides of that equation by resistance and have current multiplied by resistance is equal to voltage, which is the voltage drop across a resistor. And I'm going to count this as something explained rather than something new, since I'm just rearranging that equation. Let's start with the easy cases first, and the easiest situation is if all three switches are open, I don't have a complete circuit, and no current is flowing. And if we close just switch 1, we have two resistors connected together in series, and they're both 15.5 ohms. So 15.5 plus 15.5 is 31, and then current is voltage divided by resistance. So we have a current of 120 divided by 31, which is roughly 3.87. The next easiest situation we have is if we have switch 2 closed and the other two switches open. This gives us a circuit with one path that goes through a red resistor, a green resistor, and then another red resistor before returning to the power supply. So we've got 15.5 plus a 12.1 plus a 15.5, which gives us a resistance of 43.1 ohms, and the current flow is going to equal 120 divided by 43.1, or about 2.78 amps. The last of our easy situations is if we only allow current to pass through switch 3, in which case we have 4 resistors in our path, and once again we just add them all up. There's two 15.5 ohm resistors and two 12.1 ohm resistors for a total of 55.2 ohms. And the amount of current flowing through is 120 divided by 55.2, which is approximately 2.17 amps. So with the easy ones out of the way, let's take a look at what happens when you have switch 1 and switch 2 closed. I've redrawn the situation a bit below. We have two current paths now. One passes through one resistor and the other passes through two. And then they combine again at the bottom to both pass through a single resistor. At the top we have 120 volts. At the bottom we have 0 volts. And in the middle we have, we have to have the same voltage on both sides because they're connected by the same wire. So the voltage drop on the left must equal the voltage drop on the right. Whereas I've put it in this slide, the voltage there is 120 volts minus the voltage drop on the left, and that has to be the same as 120 volts minus the voltage drop on the right. So earlier I mentioned that voltage will drop as current travels across a resistor, and on the switch 1 side we have that voltage drop as being equal to the current going down that side multiplied by the resistance, which is 15.5 ohms. So we have voltage equals your current times 15.5, and on the switch 2 side, well, in the previous slide I pointed out that those two resistors there were in series, but neglected to say anything about that at the time. So we add the two resistance values there and wind up with a total of 27.6. And we know that the voltage has to be equal on both sides. So we have 15.5 times the current going down side 1 being equal to 27.6 times the current going down the switch 2 side. And I'm just going to solve that for I1 just because I know I'm going to need to use that to simplify later. Then we have the resistor at the end, and the voltage drop across that is equal to 15.5 times the current going down the switch 1 side plus the current going down the switch 2 side. And I'm going to bring in the I1 equals 27.6 I2 divided by 15.5 that I found earlier into this, and get rid of that I1 so we have the entire thing in terms of I2. And once you multiply the 15.5 out in the brackets, you get rid of the divide by 15.5 and you're neatly left with the voltage drop equals 27.6 plus 15.5 I times I2, or 43.1 times the current going down the switch 2 side. So 120 volts equals the voltage drop across the resistor on the switch 1 side plus the end resistor voltage drop, or which is also equal to the voltage drop across the switch 2 side and the end resistor voltage drop. And since we got everything in terms of the amount of current going through the switch 2 side of the circuit, let's go with that. So the voltage drop going across the switch 2 resistors was 27.6 times the current going through the switch 2 side, and the voltage drop going across the end resistor we found was 43.1 times the switch 2 side current, which adds up to 70.7 times the switch 2 current side. And we can just divide 120 by 70.7 to get 1.697 or thereabouts amps going down the switch 2 side. Of course, what we want is the total current where the meter is, which is the current going down both the switch 1 and switch 2 sides. So let's bring back the I1 equals 27.6 I2 divided by 15.5 equation that I wrote down earlier, and we'll substitute in the value that we found for I2, and that gives us a value of about 3 amps going through the I1 side, which means the amount of current flowing through where the meter is roughly 4.72 amps. The next scenario I want to take a look at is if you've got switch 1 and 3 turned on and switch 2 off. Once again, I've redrawn the situation below, and you can see that instead of having 2 resistors in series on one side now, we've got 3. And since those are all in series, they can easily be added together and we'd have the equivalent of 1 resistor there. And we can basically just repeat what we just did, but that would be boring. Instead of being boring, let's pull out the parallel resistor equation, and I'm going to show you where it comes from instead of saying just take my word for it. So going back to current being equal to your voltage divided by resistance, your equivalent resistor of two resistors in parallel will have the equivalent current flow being the current going down 1 plus the current going down resistor 2, which is conveniently the voltage divided by resistor 1 plus the voltage divided by resistor 2. So now we're solving this equation for your equivalent resistance, and we're going to start by dividing everything by voltage, since that is the numerator on top of all of these fractions, and that'll get rid of that. So we'll wind up with something where we've got your equivalent resistance being equal to something with R1 and R2 in it. So after removing V from the equation, it looks pretty clean and it's nice, but I'm going to multiply the whole equation by your equivalent resistance, the resistance of resistor 1 and resistance of resistor 2. And that's going to give us this big ugly thing, which has a lot of terms we can cross off, like the resistance of, the equivalent resistance divided by equivalent resistance is going to be 1, so we're left with R1 times R2 on that side, and, well, so on and so forth. It simplifies to this thing, which we can then factor out our equivalent resistance there and divide R1 and R2 by R1 plus R2. And that is how we combine two resistors in parallel as one equivalent resistor. And now that we've got that tool, we can say R1 equals 15.5, and for R2, I gave you the equation for resistors in series earlier and said just trust me on that one. So we can put down R2 as being equal to 15.5 plus 12.1 plus 12.1, which equals 39.7. So if we plug those into the equation we derived earlier, we get our equivalent resistance as being 15.5 times 39.7, all divided by 15.5 plus 39.7, which is around 11.1 something. And now we can do resistors in series again and add 15.5 to that to get 26.6 something, and 120 divided by the 26.6 something gives us a current of about 4.5 amps. So there's two more scenarios left, and for the one with switch 1 open and switch 2 and 3 closed, it's basically the same as what we've been doing. We've got two parallel resistors, and instead of one resistor at the end, we have two, but they're in series, so we just add the resistances and we wind up with one equivalent resistor again. And rather than actually do that, I'll just say it's about 3.2 amps. Let's move on to the more interesting one where all three switches are turned on. Let's start this one in the switch 3 corner. Those two resistors in the rectangle are equal to one 27.6 ohm resistor. That's in parallel with the red resistor on switch 2. So we can combine that for an equivalent resistor of about 9.925 ohms. The green resistor is in series, so we add that, and we're now at about 22. And if you feel you need to know how the last one is done, you can add one red resistor in series now and divide. Of course, right now we want the other red resistor first, which is in parallel, and that gives us an equivalent resistance of about 9.1, and I'm getting the feeling that I am going to sound so very disjointed when this is all put together. I can't wait to see it. That last resistor is in series, so we can just add that to get to about 24.6. So to wrap this up, we need to divide voltage by resistance, and we get a current of about 4.9 amps. And now I have a lot of editing to do, and let's see how this thing turns out.